All right, so we've just looked over the solution. Your next homework assignment is due on Wednesday of this week, so please upload your solution to Blackboard before class on Wednesday. And your final project report is coming up as well. I finished grading all of the reservoir submissions. I think I have. Yeah, I think I have. I think I've graded them all. So there were just a handful of students who need to review and fix there, but the final project report should be pretty polished. It should be a nice looking document, something you're proud of. Some students have taken to creating like a portfolio of their work to give to a potential employer. You know, just to give them a writing sample, to give them an idea of what sorts of figures the student is able to generate, just an illustration that they've been through an iterative design process before. So make this report nice enough, and it's the sort of thing that you could show off to someone who wants to consider you as a professional engineer employee. And then it'll also make it nicer for me to read. All right, today we're going to continue talking about hydraulic jumps, chapter 13 in your book. And you remember last time in class we talked about a momentum depth diagram, and where we got was this hydraulic jump example. And so we're going to work through that example now. This equation that's on the screen, and I'm circling with the laser pointer, the Bellinger momentum equation solves numerically what we also looked at solving graphically when it came to that Excel spreadsheet version of the momentum depth diagram. So you can create a momentum depth diagram, or you can solve the Bellinger momentum equation. Here we have an upstream depth of 0.86 meters. It's a rectangular channel, thank goodness. That makes things a little bit easier for us. It makes it easier, for example, to calculate the Froude number. So we've got a rectangular channel. We want to find out, number one, what will be the downstream depth after it goes through this rapid transition, and then what fraction of the initial energy was lost. So when you solve for the delta E, you're going to get length. This will have units of length, and so it will tell you how many meters of energy was lost. That's the delta E. So the question is, how much energy was there initially upstream? And then a fraction of the initial energy. We're just going to express that as a percentage. So the loss relative to how much energy was there at 1. But the first step, just apply this equation to solve for y2. And off on the right-hand side of the screen, I've got a couple of equations that show how you can calculate the Froude number. And since this is a rectangular channel, you can use the lower of those equations that allows you to find the Froude number in a little bit easier way. So I'll pause for a moment. You calculate that downstream depth, and then we'll take a look at the answers together. All right. So here are our calculations for the hydraulic jump. The width of the channel is given as 9.4 meters, the flow rate 123 cubic meters per second, and then the depth upstream 0.86 meters. So to find the downstream depth, we're going to need to know the Froude number at 1. That's one of the factors that goes into the Bellinger momentum equation. And so what I did was I found the flow per unit width upstream, so that's Q1, and it's 13.085 meters squared per second. I guess that'll also be the downstream flow per unit width, because the flow rate's the same and the width didn't change. Well, the depth did, but the flow per unit width won't. So the Froude number upstream is going to be 5.24, and we get the same Froude number if we use the full equation that's valid regardless of shape. This first one is, of course, only applicable if the channel is rectangular. And so the downstream depth should be 5.956 meters. Did anybody else get that same flow depth? Can anyone confirm that My number crunching isn't an error. All right, I got a couple of yeses from James and Michael. Thank you. Good. Now, of course, that's not the only Froude number, or excuse me, that's not the only version of the Bellinger momentum equation. Last time I showed you this. And so what we just solved it for was this way, but you can also calculate the downstream depth as a ratio of the critical depth and y1. So we didn't, strictly speaking, have to calculate the Froude number. You could have done the same thing by calculating what is the critical depth. But there's some expression of essentially how supercritical is the flow determines what the new depth is going to jump up to. And so we're directly solving for the momentum depth diagram, new depth. All right, now what about this part? The fraction of the initial energy that's lost. So you can calculate the energy loss in meter terms pretty easily just by substituting in the new depth after the jump and the initial depth before the jump. And of course, down in the denominator, they both appear again. So we're losing 6.4 meters of energy. Is that a lot? Well, we don't yet really have any perspective. So let's find out how much energy was there upstream before the jump occurred. And so energy is the depth and the velocity head. Not much of the energy exists as the depth. When you have supercritical flow, only 0.86 meters of energy is as depth. The majority of the energy in this example, upstream, before the jump, existed in the velocity head. And so we have 12.6 meters of energy. Almost all of that is in the velocity head because the water's moving so fast. And so we're losing 6 meters out of 12. That's a pretty substantial energy loss. On a percentage basis, that works out to about 51%. So you can see the fraction, what I've done is I've said it's the delta E divided by E1. So that's how we find out the fraction of energy that was lost in the jump. And if you have to exert the energy somewhere, like water's flowing down a spillway, it's losing elevation, picking up velocity, and that energy is either going to tear apart the channel downstream, or it's going to go through a hydraulic jump someplace in a controlled way. A hydraulic jump can be a really useful tool to make sure that the energy isn't destructive in places where it would cause a lot of damage. Any questions on this example before we move on? All right. Now, when we were calculating the momentum depth diagram, remember that one of the terms that goes into the momentum depth diagram, or the momentum function, is h bar, the depth to the centroid. So h bar is how far down from the center, how far down from the surface is it to the center of area. And for a rectangular channel, like the example that we drew up in Excel on Friday last week, it was easy because delta H was just half of the depth. But in a rectangular channel, delta H isn't going to be half the depth. Consider this. The center of area is going to be above the halfway point because more of the area is in the top half than in the bottom half. And so here is the equation that allows us to calculate the depth to the centroid. And so the area of a trapezoid is going to be its depth multiplied by the average of the width. So b top width plus lowercase b divided by 2 means the average width. That's how you find the area. But the formula that we have that describes the location of the centroid, here's a formula that describes the distance up from the bottom to the centroid. And so remember, h bar is from the surface down to the centroid. So it's top to centroid, whereas we have this equation bottom to centroid. So we'll have to keep that in mind and subtract out the distance that we calculate from the overall depth y. But here in this little illustration, just to give you an idea of how we can find the location of a centroid in a trapezoidal channel like this, Let me bring this up on screen. I won't pause because we've got a lot of ground to cover today. I'll just demonstrate that calculation for you. So if we have, as it explains in this example, a depth of 1 meter, then that means B, the top width, is going to be 5. And it's going to be 5 because the side slopes are 1 horizontal to 1 vertical. So for 1 meter of depth, then that means that we have a meter on the left side, a meter on the right side, and then the 3 meters. And so capital B is going to be 5 meters. So B is 5, Y is 1. So in this formula that was previously on the screen, Y times 2B plus B divided by 3B plus B, we calculate the area is 4 square meters, and then the depth up to the centroid from the bottom of the channel to where the centroid is located would be 0.5417 meters, and then the distance h bar would be 1 minus that. So I don't know, I don't have it written here on the PDF. I do have it on the paper copy of my notes. Let me type that in. Thus, the h bar will be 1 meter minus 0.5417 meters. And so if I just grab my calculator real quick, and that is 1 minus 0.5417, 0.4583 meters. All right, so that is depth from surface to the centroid. And why do we care? Why am I bringing this up? It's in case we are doing a momentum depth diagram. And I think you will do a momentum depth diagram with the trapezoidal channel. I just predict that. Any questions on this illustration about how you would calculate the depth of the centroid for a trapezoidal channel? I sometimes have the good folks at Walmart make a cake to celebrate hydraulic jump day. Hydraulic jump day has been canceled this year though, so no cake for you. No cake for you. All right. Yeah. All right. Here is the equation that shows us how we can find the mail it. That would be delicious. It's Walmart cake to begin with, so, you know, it's not good when it comes out of the oven, much less mailed. Here is a graph that explains how much energy is going to be lost in a hydraulic jump as a fraction of the Froude number upstream. And what you see is that in this this curve, what percent of the energy is lost in the hydraulic jump as a function of the Froude number on the horizontal axis. And so what we were just looking at had a Froude number of around 5, and we saw about 50% energy loss in the hydraulic jump. So there's a figure in your table that describes that. The next thing that we'll look at is where the hydraulic jump occurs. And a hydraulic jump coming out of an underflow gate is what we'll use as the example. And so you can see here on the screen, I'm calling this the ideal case. And what happens is the water is backed up behind an underflow gate. So the depth upstream of the gate is subcritical. And there's enough energy there that it's pushing the water under the gate at a really high velocity because of the pressure at that depth. So the water is pushed under the gate with a high velocity but a low depth. And it can't support supercritical conditions on this mild slope. In the class previously, I showed you some cross-sectional views, and a mild slope is when the slope is less than the critical slope. And so S naught is less than S sub C is a mild slope. So ideally what happens is the hydraulic jump sets up immediately after the underflow gate. Now you see a warning here in red. It says warning, new variable definitions. And the reason why I mentioned that is that now we're going to, when we talk about the location of the hydraulic jump, we're going to say instead of y1 and y2, because here in this equation, in the hydraulic jump equation that I'm showing you on this screen right now, y2 means the depth after the hydraulic jump. So y1 is upstream, y2 is downstream. Well, when we talk about the location of the hydraulic jump, we have to get even a little more creative. And so in this figure, what I mean by y prime 1 is the depth after the hydraulic jump, and then y2 means the normal depth that the channel can support. I'll show you a couple of cases that helps to clarify why this is important. But ideally what happens is that the rating curve for the channel and the rating curve for the hydraulic jump are on top of each other. They coincide. And a rating curve is just a figure that you could put together that says what's the depth versus flow rate relationship. And so here's an example of the ideal case where the tailwater rating curve and the hydraulic jump rating curve coincide. The tailwater means the channel downstream. So we could do a Manning's equation type analysis, and we could find out for a variety of different flow rates in this downstream location based on what the channel is made out of would give us an n value, the slope would be given, the flow rate is known, and so we could find a bunch of different depths as a function of flow rate. And so we could have Q versus depth, and that's what the tailwater rating curve would be, is the graph of Manning's equation, depth versus flow rate. Well, the hydraulic jump also has a rating curve. It's a hydraulic jump rating curve describes how deep the flow is going to be for a certain flow rate. And when the two are on top of each other, then the hydraulic jump occurs immediately. It occurs immediately after the underflow gate. Now, what will happen is sometimes those two curves don't line up. So here, now in comparison to the ideal case where the jump occurs immediately, the downstream jump just means that the hydraulic jump based on the depth of flow prior to the jump, the hydraulic jump wants to go up to this depth, but it can't immediately jump up to this depth that's shown y prime 1 because the channel has a different slope. So the channel is steeper, meaning that the tailwater rating curve is going to be different than the hydraulic jump rating curve. So if the tailwater normal depth is less than the conjugate depth of the hydraulic jump, then the jump moves downstream. And if we were in the lab today, what I'd do is I'd turn on the bench and I would show you the hydraulic jump coming under the underflow gate, and then I would increase the slope of the channel to make the jump move away from the gate. And so this is called a running jump, or it's just that the jump has moved downstream. So if we look at the rating curves, the jump rating curve, the hydraulic jump rating curve is higher than the tailwater rating curve. Now think about what that means. It means for a certain flow rate, you need less depth for the tailwater than you need for the hydraulic jump. So the hydraulic jump can only jump up to, is there a good YouTube video? Not specifically, no. Maybe I should make one, right? So the jump will move away from the gate if the tailwater is more efficient than the hydraulic jump. That's basically what we see here. Efficiency is what depth is required for a certain flow rate. And in this case, the channel is more efficient than the hydraulic jump, and so the gradual increase in depth has to occur until it finds the sequent depth that coincides with the normal depth in the channel. So basically, y2 without the prime, that's the normal depth of the channel, and the jump will occur when you find the sequent of the normal depth. So that is when you have a downstream jump, but the opposite of that can also happen. What if the tailwater rating curve is above the rating curve of the hydraulic jump? So the jump moves upstream if the tailwater normal depth is greater than the conjugate depth of the hydraulic jump. And so if we look at the figures here, it's saying that the tailwater is less efficient than the hydraulic jump. So less efficient means that the water has to be deeper than it ordinarily would if it was more efficient. And so you'll notice that on the screen, Y2 is pretty deep. It's deeper than what the hydraulic jump wants to come up to. If it was going to do this immediate jump right after the underflow gate, then it's looking for the sequent of Y1. So the sequent depth of Y1, Y prime 1, is the new depth that has the same amount of momentum function. But the channel isn't as efficient, and so the depth is greater, and this is drowning the hydraulic jump. So the hydraulic jump is submerged or drowned in this case. And so you actually don't even see it. It would just look like kind of a ripple on the water. The hydraulic jump wouldn't be well defined and visible. So I'd really encourage you to read through the section in your textbook. And now if you're not the type of person who generally is following along in the book with the lectures, this is one where the book can provide a lot of value, because I think that it goes to pretty good lengths to make this phenomenon clear, the forces that cause the location of the hydraulic jump to change. And predicting where it occurs is really important in the real world. If you're putting a spillway in, you want to be able to predict where the hydraulic jump will occur, because you're going to have to armor that area with a reinforced concrete to make sure that there isn't scour of the channel. So this is an important topic, and we've just kind of scratched the surface, and I could repeat this a dozen different times, but the fact remains that it really would be a good use of your time to read through the applicable section in Chapter 13. Now, the size of the hydraulic jump depends on how supercritical conditions were prior to the jump. So here we're just looking at an illustration that says we have an upstream location that's supercritical, a downstream location that's sub, and so it goes through a jump. And this looks pretty dramatic. The Y2 is so much bigger than Y1. So why is it jumping up so high? Well, it's because the bigger the Froude number, the larger Y2 is going to be. Think about algebraically, when we move Y1 over to the right-hand side of the equation, then what determines Y2 is just how big the Froude number is. So how supercritical are conditions? And if it's really supercritical, then the new Y2 depth is going to be large. And we can see that effect graphically with a momentum function. Let's say, for instance, in this figure, what is the critical depth? So critical depth is the point that corresponds to the furthest to the left on this momentum diagram. And so if I find that point and then go over to the side, it looks like it's 0.6, 7, 0.8 is the critical depth. So 0.8 is the critical depth. That's just to reiterate that we can find the critical depth off of a momentum depth diagram. All right. Next, if your actual flow depth is 0.6 upstream, then what would be the downstream depth? All right, so follow along with me. If we have a depth of 0.6, we would go over to the curve and then up and find where's the other crossover point that has the same amount of momentum. And then back over to the left-hand side, it looks like it would be 1.05. So here is the point that has the same amount of momentum. Our first depth of 0.6 and 1.05 would be the sequent depth. So that's not a very big change from 0.6 meters to 1.05 meters. But what if they're both close to each other because the upstream depth was barely supercritical. The Froude number was greater than 1, but not a lot greater than 1 in this first example. But what if our upstream depth was 0.3? Well, it's going to jump up to a more dramatic downstream depth. So follow along. If you have your beginning depth equal to 0.3, we would go over, up. The length of this line represents how big the hydraulic jump is. And so it's jumping from 0.3 meters all the way up to more than 1.7. So the new downstream depth is going to be dramatically deeper because the Froude number was larger in that second case. When your depth is 0.3, you're further away from the known critical depth of 0.8 meters. So just think about the Bellinger momentum equation. What that's saying is that the size of the jump depends on how supercritical conditions are upstream. So we can classify hydraulic jumps based on how big the Froude number is upstream. An ungular jump is so subtle that you maybe wouldn't even notice it. It could just look like some ripples on the water because the Froude number between 1 and 1.7, the upstream and the downstream depths are so close together that it's not an abrupt transition that maybe is even obvious. Sometimes the surface undulations that are shown could be bigger than the change itself. We call it a weak jump when the Froude number is between 1.7 and 2.5, and the length of the rolling surface is small relative to the jump length, and so that's a weak jump. The thing that is important to look at in both of these figures so far is the arrows, because what we prefer is a hydraulic jump that doesn't have much velocity going down into the channel bed, because the velocity going down into the channel bed can cause scour of sediment. And the oscillating jump is one that could give us some trouble, because in the oscillating jump you see that some of these velocity vectors are going down towards the channel, some of them are countercurrent, and so this is considered a destructive hydraulic jump. And in design, where you're trying to force a hydraulic jump to occur, then this is one that you'd have to be pretty careful about. You wouldn't want it to stay in the oscillating range for very long or for a very large flow rate range. Stable jumps are preferred because if you look at the velocity arrows here, none of them are going down into the channel. They're going up through the water, and so the energy is being dissipated into itself instead of there being a big exertion onto the of shear stress onto the channel. And so a stable jump with a Froude number between 4.5 and 9 is considered pretty advantageous. You're having a big transition in the depth, and the jump location is insensitive to variation in the depth, and so where the jump sets up isn't going to be as affected by the changes in downstream depth. And then when you go beyond a Froude number of 9, that's considered a strong or a rough jump, and there can be a pretty enormous variation, the ratio of depth between 12 and 20, and so stilling basins would be required to kind of smooth and quiet the water before it enters any kind of a natural line channel. The Bureau of Reclamation is a federal agency that's kind of the equivalent of the Army Corps of Engineers in the western part of the United States. Their missions don't overlap with exact precision, but the Bureau of Reclamation has responsibility for managing water resources and rivers and reservoirs in the West. And so they have a publication that describes the length of a hydraulic jump as a function of the Froude number. And so if you know the Froude number of a hydraulic jump, what you can do with this figure is you can go up from the Froude number, find this curve, go to the vertical axis, and then what this ratio is describing is how long the hydraulic jump will be relative to the depth downstream. So L sub j is the length of the jump, where here this L sub r is referring to the length of the rollers. And so sometimes people mistake seeing just the visible turbulence in the water and the air that's entrained and thinking that that's the jump. But the jump continues beyond where the rollers are visible a little bit further. And so this nomograph and other approaches like it have been developed to try and estimate what is going to be the length of the jump. One approach for estimating the length of the rollers is that maybe it's about 40% of the jump length. In addition to the Bureau of Reclamation nomograph, the Hager equation can describe or estimate what the length of the hydraulic jump will be. And here you can see we're using the hyperbolic tangent equation, which is kind of a rare application of that, with the Froude number going in. That would be another way to describe the length of the hydraulic jump. And then our textbook equation just says, and there's also another jump equation, without giving the name or saying where it comes from. But since it's in the book, a simpler way of estimating the hydraulic jump length would just be the ratio of the depths and then some constant factor, which our book says varies from 5 to 6.9. It is 1:49, so we will pick back up on Wednesday's class here with this example where we will find the length of a hydraulic jump using the Hager equation, using the nomograph from the Bureau of Reclamation, and also using the another equation. So we'll have to wait for that, but before we part ways, just one last look at the announcements that the homework assignment is due on Wednesday, and then the next thing on your to-do list following that homework assignment is the final project due on Monday. So that's it for today. If you have any questions, you can email me, or we can set up a time to have a meeting maybe here in the Collaborate classroom. So let me know if there's anything I can help you with, and I hope you have a great day. Bye-bye.